exponential growth and decay is one common application of differential equations. Another common differential equation is what's known as the logistic differential equation. So we'll start with this example here and use it to kind of help motivate the ideas that we're dealing with. So we have P, which is the number of squirrels in a forest, T months after the year 2000. Okay, it turns out that the population, somebody discovers that the population grows according to this model. So the rate at which the number of squirrels is changing is 0.045 multiplied by P. So if you just stop there, that would be an exponential growth problem, wouldn't it? Because the rate at which the squirrel population is changing is proportional to the population. But we're going to add on an extra little factor which kind of keeps things in check, which is 1 minus the population divided by 5,500. Okay, so at some point you probably learned that an equilibrium solution is a function, in our case it would be a function p, that would make the derivative 0 everywhere. So we want to know what the equilibrium solutions are for our particular function. Well, in order to make the derivative 0, we would end up with this equation. 0 equals 0.045p times 1 minus p divided by 5,500. When we have a product of things equal to 0, some factor has to equal 0. So either 0.045 equals 0. Of course, that's not going to be true. P could be 0, though. That's the second factor in this business. Or this last factor could be 0. So 1 minus P divided by 5,500 might be 0, which would mean that 1 is equal to P over 5,500. So P equals 5,500. If you multiply both sides by it, that would be another equilibrium solution. And so I have here the direction field as well as one possible solution drawn. So remember, direction fields are kind of like water currents, and when we drop a cork in a particular place, we just follow the currents. So the way this is drawn is someone dropped a cork down here. Can't really read what that is. That looks like it's at about 500 or so. And when we did that, we follow the current, and it's getting very steep here, but notice it's not quite so steep as we move on out this way. Okay. Now, P is this axis, the vertical axis. T is the horizontal axis. Okay, so P equals 100 would correspond exactly to the t-axis. Let's color that in green. P equals 5,500. It's hard to read this, but this is 2,500. That's 5,000, so 5,500 is right here. That's the other equilibrium solution. And notice that just below that, the dashes are almost horizontal. Just above it, they are almost horizontal, but they're decreasing. And notice what our function did. Our function went along and kind of hugged that. Okay, so let's ask this question. Suppose P of 0 is 1,000. So that means when at time 0, we have 1,000 squirrels. Is the population increasing or decreasing? Okay, so think back to your Calculus 1 days. How do you know if something is increasing or decreasing? You look at its derivative. So let's look at the derivative evaluated at 100. If I do this, let's see, I'm going to try to squeeze it in here. dp dt will be 0.045 times 1,000 times 1 minus 1,000 divided by 5,500. Now we don't have to calculate this, let's just analyze it. 0.045, that is a positive value. Right, that's a positive value. 1,000 is positive. How about this last factor? Well, 1,000 divided by 5,500 is less than 1. 1 minus a number less than 1 will also be positive. So all over the place, this function, this derivative actually, is positive And if it's positive, we are increasing. And you can kind of see this from if we start at 1,000, 1,000 is right here. Well, those dashes are going up. It will look something like that. How about if it's 10,000? Well, let's do the same analysis. dp dt is still 0.045. Now we multiply by 10,000, and then we have 1 minus 10,000 divided by 5,500. Let's go factor by factor and determine their signs. 0.045 is still positive. 10,000 is a positive number. And, 10,000 divided by 5,000 is almost 2. It's definitely bigger than 1. If we take 1 minus a number that's larger than 1, we end up with a negative number. So overall, this is going to be negative, which means we are decreasing. And unfortunately, we can't really see it, but you can look at some values above 5,500. If I'm up here, those are decreasing since they have a negative slope there. So this is an example of a logistic differential equation. We'll talk more about them, how to solve them. Actually, not really how to solve them, but in a sense how to solve them. We'll use formulas rather than actually doing the differential equation work. But they're kind of nice little things. They help model things like population growth, the spread of rumors, the spread of diseases, and so forth. So this is what it will look like in general. It's a logistic differential equation if the rate is a constant multiple of the function. Okay, kind of. We've got a little bit of a fix there. That would be exponential growth as we had in the previous example. We also have this extra factor of 1 minus p over m. Now I will say that they're not always given to you in this particular form. Why are these special? The relative growth rate of any particular function is the derivative divided by the function itself. So here is the derivative multiplied by 1 over p. An example I gave in the exponential growth and decay is a city. If a city is growing by 500 people per year, that's much more significant if we have a city of 2,000 people than if we have a city of 2 million people. So that's what the relative growth rate is doing. For exponential functions, we stop at k. The relative growth rate is a constant. Well, if I do 1 minus p over m, it's not constant, it's actually a linear function in the function itself. It's linear in p. Okay, when p is relatively small, okay, relative to m. So if m is like 5 million and p is 10, if m is 5 million and p is 10, then this quantity is almost 0. P over m would almost be 0. In which case, we would have 1 minus 0, which is just 1. We get something that's pretty darn close to exponential growth. Okay, in which case the relative growth rate is constant. We call m the carrying capacity because when t approaches infinity, p approaches m. Okay, that's what's known as the carrying capacity. How much can it sustain? An island can only sustain so many squirrels. If there are too many, we'll have too much competition for food. If there are very few squirrels, there's room for them to grow. So we're not going to go through the derivation of this, but I'm going to give you a picture of how we would do it. Let's suppose we want to solve this differential equation. Remember, we do this by separation of variables. You can do a little bit of manipulation of fractions inside of here. And there is no t whatsoever. So we'd multiply both sides by t. Maybe we can keep the k over there with the dt. Divide both sides by p. The dp remains. And then this stuff becomes m divided by m minus p. We want to integrate this with respect to p. It is a rational function in p, so we would use partial fractions. And it turns out when you do it, you end up with something like the natural log of p minus the natural log of m minus p is equal to k times t plus c. That's pretty easy to see. Okay, so when you solve for p using properties of logs and the exponential function, you end up with something like this. You would first combine these two with a log property then use the exponential function. Now you might ask, what happened to C here, and where in the world did A come from? Well, the C and the A are related. When we do the exponentiation, you'll end up with something like e to the c, and you can multiply that by something. So that's, we generally take e to the c, multiply by something, and replace it by a different constant. In this case, we replace it by a. So that will be the solution. So the question is, how do we get a? The next slide gives us all the information we need. This logistic equation, dp dt equals kp times 1 minus p over m. If the initial population or initial value is p0, your solution is the carrying capacity divided by 1 plus a, which we'll discuss in a minute, e to the negative k. Well, the k is right there, multiplied by t. Where does a come from? A, you have to know this formula. A turns out to be m minus the initial population divided by the initial population. So here's the way I like to look at this. Let's imagine the graph. The graphs look something like this. The carrying capacity is up here. And we saw they have this S-shaped curve to them. Now I drew my initial value very, very low there, P0. A, well, it says it's m minus P0 divided by P0. P0 is pretty easy to depict. We're moving up and down. That's the value for P0. How about m minus P0? M is up here. M minus P0, m is a y value, P0 is a y value. So m minus P0 is that distance. So in a sense, A is the ratio of how far we have to get to the initial population, or from the initial population to the carrying capacity, divided by how far we've come. How far do we have to go, divided by how far we've already come. Okay, so we have a small college, and there is a rumor going around. The percent of students who have heard the rumor is given by this logistic differential equation. Now, our general form for these is dp dt equals k times p times 1 minus p divided by m. Is ours in that form? Well, it looks like it because we have k there times p times 1 minus p over m. Okay, so what percent of the population will eventually hear the rumor? Well, looks like that's the carrying capacity, which is 75. Now you want to go from context. We're talking about percentages here, and sometimes we say, well, you got to move the decimal point. In this case, we already are discussing this in terms of percentages, so there's not a decimal point to move. If you did, that would be 700 or 7,500%, which makes no sense. Okay, so on day 0, the first day that is, only 1.5% of the student population has heard the rumor. We want to know what the formula is for the percent of students who have heard the rumor T days after the rumor starts. Okay, so we know that the formula is P equals m divided by 1 plus a e to the negative kt. We know m is 75. We also know that k is the coefficient of p, so k is 0.023. We don't know what a is, though. Those are our parameters. P and t are our variables. A, m, and k are our parameters, which once we know, they are fixed. Okay, so we know that p or m will always be 75, k will always be 0.023 for this particular problem. We just need to figure out what a is. Again, a is how far are we from the carrying capacity. That's m minus p0, divided by how far have we already come. Well, m we said was 75 minus 1.5%. 1.5 divided by 1.5. And this equals 49. So our equation is going to be P equals our carrying capacity 75 divided by 1 plus A, 49, e to the negative 0.023 t. Okay, so on what day will 25% of the population have heard the rumor? On what day means we are looking for t, so we're going to find out when is p equal to 25. So we have 25 equals 75 divided by 1 plus 49 e to the negative 0.023 t. If I multiply both sides by the denominator and divide both sides by 25, we end up with 1 plus 49 e to the negative 0.023 t equals 75 divided by 25, which is 3. Nice round number there. Subtracting 1 from both sides, 49 will e to the negative 0.023 t is going to be 2, subtracting 1. Now if we divide by 49, we get e to the negative 0.023 t equals 2 49ths. We'll take the logarithm and divide by negative 0.023. And so it will take about 139 days in order for the 25% of the population to have heard the rumor. For our next example, we have dp dt equals negative 0.1 or 0.1 p minus lots of zeros, 5 p squared, with an initial condition of p of 0 equals 150. Once again, let's remind ourselves of the formula. It is dp dt equals k times p, 1 minus p divided by m. Okay, so this is going to be a little bit more challenging, but it's not too bad. If I look at this, this looks like a quadratic in p, doesn't it? P and p squared. That's not the way this is written, but it truly is a quadratic. We would get that if we distribute the p through. Well, the opposite of distribution is factoring. So what I'm going to do is I'm going to factor so that I have a 1 minus something. Okay, the kp and the p over m would give me the p squared. So I'm going to factor out this whole quantity. So that's going to give me dp dt equals 0.1 p. We factor out the 0.1 p, we'll get 1 there. And then when you think about this, factoring, you divide. I would divide this 0.00005 by 0.1. Well, 0.1, if we read it correctly, is 1/10. If you divide by 1/10, that's the same as multiplying by 10, which is going to give us 0.0005 p. Okay, and now this is where things get a little bit wonky. We want it to be in this form, 1 minus p over m. I have 1 minus something times p. Okay, if I ever want to move something to the denominator, the standard tactic for doing that is to take its reciprocal and stick it there. So we'll end up with 0.1 p times 1 minus p divided by 1 over 0.0005. Okay, that's kind of messy. But that's the way it'll work, right? Because if I divide p by a fraction, p divided by a fraction, you divide or you multiply by the reciprocal of the denominator, which would get us back to this stage. And when we calculate that denominator, we end up with 0.1 p times 1 minus p divided by 2,000. So we were asked the carrying capacity, and it's kind of nice that we ended up where we did. The carrying capacity is the denominator here, and our denominator is 2,000. So our carrying capacity is 2,000. Okay, we want to use the formula the logistic differential equation to write a solution to the differential equation. I remember that the formula is P equals m over 1 plus a e to the negative kt. I know what m is. K is the coefficient in all of this business, so this is going to be my value of k. A, we have to figure out. So I'm going to start writing it all in. This equals m, which is 2,000, over 1 plus, okay, I'll take a break here. A was the ratio of how far we have to get to the carrying capacity from our current position, the initial value, divided by our initial value. So in our case, that's 2,000 minus, we are currently sitting at 150, and we're going to divide that by 150, which is equal to 37 over 3. I'll keep it a fraction. I can handle the fractions. 37 thirds e to the negative k. K is 0.1, negative 0.1 t. What is P of 10? Okay, now there's no context here. No squirrels, no rumors, no diseases, no bacteria, nothing. P of 10, all we have to do is substitute 10 in for t. So we have P equals 2,000 divided by 1 plus 37 thirds e to the negative 0.1 times 10, which is approximately 361.19. Okay, again, we don't know what we're dealing with, so I did do some decimals. If these were turtles or something, of course, I would round to 361. Okay, so what rate is the population changing when time is 10, when we're at time 10? Now, if you watch the exponential growth and decay video, there's something similar to this. At what rate, we're talking about derivatives, is the population when time is 10? Well, we just figured out what's happening at time 10. Okay, we know what the population is at time 10. We know what the population is, but we don't know at what rate that population is changing. Okay, so we have this lovely differential equation now. I know that P is equal to 361.19 when T is equal to 10. And so if I want the derivative at that particular time, I can go all the way back to the original, or one of our factored versions, differential equation, and stick in that number for T, or for P. So dP dt, the rate at which the population is changing, is going to be 0.1 times P, which is 361.19, minus 0.00005 P squared. P is 361.19. We're going to square that, which is approximately 29.60 something per something. We don't have units for P and T, but that's the rate at which the population is changing when T is equal to 10. So watch out for those kinds of questions. When you're asked to find the population at a particular time and then asked to find the rate at which it's changing at the same time. Most likely they're looking to see if you can recognize the relationship between the differential equation and what you're looking for. Okay, so we're back to squirrels. We have a forest with 1,500 squirrels, and biologists estimate that the carrying capacity is 12,000. I'm just going to go ahead and say, ha, M is 12,000. The number of squirrels doubled in 5 years. Oh, okay. So when T is equal to 5, the number of squirrels has doubled. So now instead of being at 1,500, we're at 3,000. We are assuming that the population of the squirrels is modeled by a logistic function. We want to find an equation for the population after 2 years. This is slightly different. It's going to require a little bit more algebra, but we can do it. We do not know what A is. We can figure out what A is, can't we? I guess A, remember, was M minus P0 divided by P0. M was 12,000. P0 is 1,500. And we're dividing this by 1,500. And this equals 7. So we can put everything in except for K. P equals M, 12,000, divided by 1 plus A, which is 7, e to the negative K times T. Okay, we're going to use our extra piece of information here that when T is 5, P is 3,000. We're going to use that to figure out what K is equal to. So we'll put 3,000 in for P. That's 12,000 divided by 1 plus 7 e to the negative T is equal to 5, so 5 times K. I'm going to multiply both sides by the denominator. Multiply by the denominator and divide both sides by the 3,000. That'll give us 1 plus 7 e to the negative 5k equals 12,000 divided by 3,000, which is easy to calculate. That's 4. If we subtract 1 from both sides, we end up with 7e to the negative 5k equals 3. Divide both sides by 7e to the negative 5k is 3/7. We will take the natural log of both sides and divide by negative 5. And we end up with k equals negative 1/5, natural log of 3/7. If you need to, pause it for a moment. We'll put this into the equation. We get that p equals 12,000 divided by 1 plus 7 e to the, okay, we've got to be super careful here. It's e to the negative k, and k already has the negative inside here, okay? And there's the negative there. So those two will cancel each other out. And so we end up with 1/5. Let's go back to black here. 1/5 e to the negative k. K is 1/5 natural log of 3/7 multiplied by t. And I'm going to combine the e and the natural log of 3/7. E to the natural log of 3/7 equals 3/7. So we get p equals 12,000 divided by 1 plus 7 times 3/7 to the t divided by 5. Where did that t over 5 come from? It came from what was left in the exponent there. There are properties of exponents which allow us to bring the e to the natural log of 3/7 to get 3/7, and then the remaining will be the exponent. All right, so finally, how long will it take for the population to reach 5,000? We want an exact answer and one accurate to 3 decimal places. So if p is 5,000, we'll get 5,000 equals 12,000 divided by 1 plus 7 e, well, no, not e this time, 3/7 to the t divided by 5. And then let's see, we'll multiply both sides by the denominator and divide by 5,000. 1 plus 7 times 3/7 to the t over 5 is 12,000. I'm sorry, yep, 12,000 divided by 5,000. Well, we can divide by 1,000 and we get 12/5. Subtracting 1, 12/5 minus 1 is 12/5 minus 5/5. So we get 7 3/7 to the t over 5. 12/7 minus 1 is 7. 12/5 minus 1 is 7/5. Dividing by 7, we'll end up with 3/7 to the t over 5 equals 1/5. We can take the natural log of both sides and bring down the t over 5. T over 5 ln 3/7 equals natural log of 1/5. And when we multiply by 5 and divide by the natural log of 3/7, we'll have 5 natural log of 1/5 divided by the natural log of 3/7. which is approximately 9.497. So our exact answer is this one with the natural logs in it, and our answer accurate to 3 decimal places is this one.